Okay, so here's another integral where we're going to use the Feynman technique of differentiating under the integral sign. Sometimes when you do this you have to insert the parameter yourself that you're going to differentiate with respect to, but here we already have a parameter in the problem, lambda. Okay, so the idea is to rewrite this integral as a function of lambda. Okay, so it's a function of lambda, and we're going to differentiate with respect to lambda. Okay, which is going to give us, there's going to be a cos x on the top, and a 1 plus lambda cos x on the denominator. Okay, now that this is a rational, the integrand is a rational function of trigonometric functions, this is doable by a very special substitution. Now, to make this a little bit easier, what I'm going to do is actually multiply both sides by lambda. Okay, and then in the numerator of the integrand, I'm going to add 1 and subtract 1. Okay, so lambda, f dash lambda. Now this whole integrand I'm going to split up. You can see that there's a 1 there, and then minus this integral here. So this wasn't strictly necessary, but it's going to make our life a little bit easier. Okay, this integral here is obviously a pi, and this integral here we're going to call I. Okay, so as a little aside, let's look at I. We're going to perform what's called the Weierstrass substitution. Okay, this is what you use for rational functions of trig functions. Okay, this is a little bit of a strange substitution if you haven't seen it before. T is tan of x on 2. Now I won't go through the details, but you can show that cos x is 1 minus t squared on 1 plus t squared. Okay, and dx is 2 dt divided by 1 plus t squared. Okay, so and the limits, okay, when x equals 0, t equals 0, when x equals pi, t is going to go to positive infinity. Okay, so I is going to become this integral here under that substitution. So this is looking like a proper rational function now. Okay, so we're going to need one more substitution to put this into a form that we can really recognize. Okay, and that is going to be t is square root of 1 plus lambda on 1 minus lambda times, say, a new variable u. Okay, this is to get rid of the 1 minus lambda, that's multiplying the t squared. Okay, so the limits aren't going to change. We will simply get that I is 2 on root 1 minus lambda squared, integral 0 to infinity of du on 1 plus u squared. Okay, so if you haven't seen this integral before, okay, it's fairly famous, is equal to pi on 2, okay, which gives this value here. Great, so scrolling back up, okay, that's going to go where I is. Okay, so we have that lambda f dash is pi minus I okay, so f dash is pi on lambda minus pi on lambda root 1 minus lambda squared. Okay, and we're trying to, we're trying to find f, so we need to integrate. Okay, here we simply get log lambda. Okay, or maybe I should use natural log because I used it before. Okay, natural log of lambda minus this integral here. Okay, so this integral is actually fairly standard. What we end up getting, so skipping to the end, is pi times the log of 1 plus root 1 minus lambda squared plus a constant of integration. Okay, so if you don't believe me, differentiate that and you should get this function up here. Okay, so what is C? To find the constant of integration, we need to let lambda be a value where we can actually figure out the original integral. Okay, so if we look at this original integral now, okay, let me write that in black. Okay, so the value that we're going to choose for lambda is lambda equals 0. Okay, so f of 0 is the integral of log of 1 plus 0 dx. Log of 0 is 0, so f of 0 is 0. Okay, so f of 0 being 0, if we put that into equation star, then 0 equals pi log 1 plus 1 plus c. Okay, so c equals negative pi log 2. Okay, so we have our final result. Okay, or if you like, this original integral we started with. Give myself a bit more room. Is this thing here. Okay, hope you enjoyed.